We're going to solve quadratic inequalities of one variable in this video, and this is kind of a challenging section, and to try to make it a little bit easier I have 4 steps that we're going to try to follow, and in order to kind of understand this I came up with kind of a basic example in this first one, and we'll just apply these steps to it and we'll go from there. I'm trying to find in example 1 when this expression x squared minus 4 is bigger than or equal to 0. So the idea is what x values will make that true. Now we can guess and check if we would like I know, for instance, just looking at this, if I plug in like 100 squared minus 4 is definitely bigger than 0, but there's many other values besides x equals 100 that could possibly solve this thing. So going about it in a more methodical way is kind of what we need to do here. First step, I'm going to solve the quadratic equation to find the zeros. It's kind of easier to look at an equation, x squared minus 4 equals 0, because that's what we spent the whole chapter trying to solve. What we could probably do here is solve by taking square roots, but since factoring is usually how we're going to solve almost all the problems, at least in my class for these inequalities, let's practice factoring. So recall, first step should be looking for a GCF, and there is no GCF of x squared and 4. But I do recognize that's a special pattern. That's a difference of squares, which x squared is a perfect square of x, so that goes in the first position, and 4 is a perfect square of 2. And remember, one binomial is plus, one is minus. If you FOIL those together, you will get x squared minus 4. Now, to get the solutions here, I have to set each of these factors equal to 0. So I have x plus 2 equal to 0, and if we subtract 2, I will get x equals negative 2 as 1, 0, and x minus 2 equals 0 when x equals positive 2. So these are 2 solutions, or zeros, to the equation. Now, keep in mind, what we've just found are 2 solutions. If I plug in either x equals 2 or negative 2 in the original inequality, you're going to end up with 4 minus 4 either way. If you square 2, you get 4. If you square negative 2, you get 4. And both of those give you 0 is greater than or equal to 0, which is true. So these are 2 solutions, but they're special because these are kind of like endpoints, if you will, of an interval where possible solutions are. And this is what I mean by that. In order to find the other possible solutions, we're going to go on to step 2 and plot the zeros on a number line. So you can see I've already drawn a number line here. And let's say we have 0, 1, 2, 3, and so on, negative 1, negative 2, negative 3, and so forth going to the left. And so in this second step, it says plot the zeros on the number line. Well, the zeros that we found in this example are at 2 and at negative 2. And I'm making these filled in circles because these are solutions. We do get a true inequality if we plug in those numbers. Now, the idea is these are all possible x values that are solutions to the number line. We know 2 out of the millions and infinitely many solutions, but what about x values that are less than negative 2? What about x values in between negative 2 and 2? And what about the x values that are greater than 2? So there's kind of 3 sections of this number line that we need to kind of check out to see if they work or not. So step 3 is kind of the trickiest step I think students have, and we're going to determine the correct intervals on the number line that satisfy the inequality by picking an x value that's less than, which is kind of over here, in between, and greater than each of our zeros at negative 2 and 2 for this example. So if I'm going to test this first interval where it's less than the 0, I can pick any x value less than negative 2. So I'm going to choose negative 3. If I plug in negative 3 into my original inequality, I'm going to get negative 3 squared minus 4 greater than or equal to 0. If I square negative 3, I get a positive 9. Having a hard time writing with this thing right now. Positive 9 minus 4 greater than or equal to 0, and that's 5 greater than or equal to 0, which is absolutely true. That tells me that negative 3 is a solution, but more important than just negative 3, I could have picked any x value that I wanted that was less than -2. There was nothing special about -3. If I plug in -4 or -5 or anything less than -2, it's going to work. So what I'm going to do to kind of signify that is shade to the left of -2. Right now I know x values less than or equal to -2 are solutions. What about in the middle though, or in between the zeros? Well, that means I'm going to test some x value in between -2 and +2. It's really up to you what you want to choose, but if you think about it, the easiest thing to substitute in is probably 0. And if you square 0 and take away 4, you're going to end up with -4 bigger than or equal to 0, which is absolutely false. That is not true. So 0 is not a solution. Neither would anything in between -2 and 2. So I know that I'm going to have to skip values in between -2 and 2. My next job is then to figure out, okay, well, what about for the values of x that are bigger than 2 over here in this interval? Well, maybe the obvious choice here is to plug in 3 or really anything you want, that as long as it's bigger than 2, you're okay. If you take 3 and square it, take away 4, you're going to end up with, once again, 9 minus 4. And you're going to get 5 bigger than or equal to 0, which is also a solution. So that tells me that 3 is also a solution here. But there was nothing special about 3. I could have picked very well 4 or 5 or anything larger than 2. So really, any of the values of x that are greater than or equal to 2 would also work. Let's clean this up a little bit. I'm just going to rewrite this number line, and we're going to relate it to something we know. So here's -2, here's 2. Those are the most important values. You're going to later learn in calculus, these are called critical values when we test points in a function. So -2 and 2 worked, and so did anything less than -2 or bigger than 2. If you notice what I just said, I said or. This is a compound OR inequality we talked about, I think, in like chapter 1 or 2. This is algebra 1, guys. I just need to describe all of these x values. Well, x values that are less than or equal to -2 describe all of these solutions. Or, because remember when there's a space in between, you use the word or, I can pick x values that are bigger than or equal to 2. That describes all of the x values over here. So as long as I choose an x value that satisfies this compound inequality, I will get a solution to the original inequality over here, which is kind of cool. Let's look at another couple more sophisticated examples to look at here. All right, here we go. Example 2. In this one, I have x squared minus 5x plus 6 bigger than or equal to 0. Do you recall the first step is to solve the quadratic equation, x squared minus 5x plus 6 equal to 0. We're going to do this by factoring, and I notice there is no GCF for these terms. So I'm going to look for a perfect square trinomial. However, 6 is not a perfect square. So perfect square trinomial is out of the question. So I could factor by grouping, but I notice that because the leading coefficient's 1, I can put just an x and an x there. Now my job is to find two numbers that multiply to make 6, m times n has to be 6, and add to make -5. And if you think about it, the values would have to both be negative, and I think -2 times a -3 is going to do the trick. That means if I set x minus 2 equal to 0, I can get 1 0 of 2. And if I set x minus 3 equal to 0, I'm going to get another 0 of 3. Remember, from here, we make a number line. And we plot our zeros on it. So I'm going to put 2 here and 3 here. Now, I'm going to test the value of x that's less than 2. Like, I could use 1, but even easier would be 0, wouldn't it? So I'm going to try x equals 0 in my original quadratic. And I think if I plugged in a 0, I end up with just 6 bigger than or equal to 0, which is true. That means anything less than 2 is a solution, since 0 worked, and it's over here. So I can shade to the left of 2. By the way, I wonder if I should put an open or closed circle on 2 here. Remember, if you plug in 2 into the equation, this is a 0, meaning the original quadratic turns into 0, and I would get 0 bigger than or equal to 0, which is a solution. That means 2 works, so I want to make that a nice closed circle there. Same thing for 3. Let's go ahead and do that before we forget. Now, if you remember, we want to check something in between 2 and 3. And you might say, well, there is nothing in between 2 and 3. Well, of course there is. There's millions of decimals we can create that are in between 2 and 3. Let's just try to use a simple one, maybe right in between, like 2.5, 2.5. So let's try 2.5. If I substitute 2.5 into the original, we're going to have to do 2.5 squared minus 5 times 2.5, add 6 to it, and see if we get something bigger than or equal to 0. If you square 2.5, I think you get 6.25, 6.25. 5 times 2.5, I think, is 12.5. So I'm going to get minus 12.5. And then we have to add 6, and it should be bigger than or equal to 0. If you add 6.25 to 6, that's 12.25. Then we have to take away 12.5, and that's going to be a negative 0.25, which is not bigger than 0. It's a negative number, so that's false. So that tells me we do not want to pick any of these decimals in between 2 and 3. Now we have to pick something greater than 3. Let's say 4. If I try x equals 4 into my original, it's going to be 4 squared minus 5 times 4, add 6, bigger than or equal to 0. That's going to be 16 minus 20 plus 6, bigger than or equal to 0. And that's going to be what? Negative 4 plus 6, bigger than or equal to 0, or 2 is bigger than or equal to 0, which I like. That is true. That means 4 is a solution, and therefore anything that is bigger than 3 is also a solution there. If you think about this inequality, or that number line rather, that's another compound or inequality, and it would go x is less than or equal to 2, or x is greater than or equal to 3. As long as I pick an x value that satisfies that inequality, it will also satisfy this quadratic inequality. Let's take a look at another one. Alright, for this guy, actually I'm going to skip that one. Let's just do one more good one that's kind of a tough one. Let's look at example 4. Sometimes you're going to get an inequality that kind of looks strange, meaning you don't have like a 0 on one side. Just remember, stick to your guns. We're going to create a quadratic equation and solve it here. So I'm going to set up 8 equals x squared plus 2x and try to solve this equation. Now, let's see. Easiest thing to do is probably to subtract 8, right? And I get 0 equals x squared plus 2x minus 8. Now this thing hopefully can be factored, and there is no GCF. It's not a perfect square trinomial because that last term is negative. That ain't going to work. But since the leading coefficient is 1, I can just drop an x and an x and look for two numbers and multiply and make negative 8. It had to be 2, and I'm thinking positive 4 times a negative 2 is going to work. They multiply to make negative 8, they add to 2. That means if I set x plus 4 equal to 0, I'll get x equals negative 4 is 1, 0. And if I set x minus 2 equal to 0, I'm going to get x equals to 2 for the other 0. Now, let's plot these. Now, these are the zeros on the number line. Here's negative 4, and 2 is over here to the right of it. Now, let's think carefully for a second with what kind of circle we should put on these zeros, whether it should be open or closed. If we plugged in negative 4 into this equation, let's see what happens. Let's see what happens. If I do x equals negative 4, I end up with 8 less than negative 4 squared plus 2 times negative 4. So that's 8 less than, that's going to be a positive 16 minus 8. I get 8 greater than 8, which is close, but it's not true. This is going to be an open circle, and likewise, so will this one. If you prefer, one way of thinking about it is like this. If you took this inequality and just subtracted 8 from it to begin with, it'd be 0 is greater than x squared plus 2x minus 8. And considering that negative 4 and 2 are our zeros, we would end up with 0 is greater than 0, which is not a true statement, right? So that's why we have to have open circles there. There still are zeros, and they're going to be part of our answer, but we don't want to include them as part of the solution. So open circles there. Now we do the same game. We're going to test something less than negative 4. Let's try x equals negative 5. Now I'm going to plug this into my original. So I'm going to do 8 less than negative 5 squared plus 2 times negative 5. And I get 8 is greater than 25 minus 10. And that's 8 is greater than, what, 15? That doesn't look good. That's not true. So I do not want to shade there. Let's pick something in between, like zeros in between negative 4 and 2. Okay, here we go. Let's try x equals 0. I'd get 8 less than 0 squared is 0, plus 2 times 0 is 0. I get 8 is greater than 0, and that looks good. To me, it is bigger than 0. So 0 is a solution, and therefore everything in between is also a solution. Let's check 3. X equals 3. If we try that guy, we're going to get 8 less than 3 squared plus 2 times 3, and 8 is less than 9 plus 6 is not looking good. That would be 8 is greater than 15, and that is not true. So 3 is not going to work. Guys, this is the inequality I want to describe. That's a sandwich or an and inequality, a compound and inequality. So if I was going to describe that, that's going to be all x values that are strictly greater than 4 and less than 2. Remember, sandwiches, the x is in the middle. We put the small endpoint on the left, the larger endpoint, 2 on the right, and we've sandwiched in between. Remember, we don't want to use negative 4 and 2. That's why I don't have the little equal to pieces on there. I would not want that. That would be incorrect. So this is our final answer, anything in between the two. Okay, hope you enjoyed the video, and it's a little bit long, but it's also kind of a tough one. We'll practice more in class tomorrow. Thanks for watching.